Hello and welcome to Chapter 9. This chapter divides up into two different PowerPoints. So in this first PowerPoint, we're mostly going to cover what are known as relative dating techniques. And just to jump into the chapter material, relative dating techniques establish the age order of different rock units and different geologic events like mountain building and faulting, etc. And so when we're focusing on relative dating methods, we're really interested in the question of older versus younger without any reference to the actual age of the geologic event or the geologic material. In the next PowerPoint, we're going to go into a lot more detail about absolute age dating techniques. And with these, we are concerned with how old a geologic event is, that is, when exactly did it happen, or perhaps how old a particular rock layer is. Okay, so these are the 6 relative dating principles you want to be familiar with. I don't so much care whether you can actually remember the lingo here. I'm not going to ask you on an exam, for example, to tell me the principle of inclusions and get the terminology right. What I'm more interested in, as we'll see, is whether you can apply these 6 different dating methods to actually solve relative dating problems. And we'll get to that in a minute. Okay, well, number 1 is what's called superposition. And this is just kind of common sense. So when you have a layered sequence of rocks like we do over here, this is the south wall of the Grand Canyon, by the way, then it's obviously the case that older layers are going to be on the bottom of the stack with increasingly younger layers higher and higher up in the stack. And this, by the way, applies not only to sedimentary layers, but it would apply to a sequence of lava flows as well. So in a stacked sequence of rocks, the younger rocks are on top, the older rocks are on the bottom. That's called superposition. Next up, we have original horizontality, and that's, again, very descriptive, kind of common sense. And this one just reminds us that when we see sedimentary layers, strata, the strata always start out close to horizontal, like we're seeing here. So again, we have some layered sedimentary rocks, and they're flat. But often it's the case that the layers aren't flat anymore. They've been tilted at some angle. And so going from here to here, then what's happened on the left is these horizontal strata have been rotated. So they're no longer horizontal anymore. The reason this relates to relative dating is it obviously means then that when we see a sequence of tilted strata, like we do on the right, that the tilting event must post-date the age of the rocks themselves. We know from modern day observations that sedimentary rocks tend to be laid down flat to begin with. And so if we see a sequence of sedimentary layers or perhaps a sequence of lava flows that aren't flat anymore, they've been tilted, that is, they're dipping, then we know that the tilting event happened after the original deposition of the layers. And again, that's called original horizontality. Okay, a lot of times we apply these different relative dating principles in concert. So let's go through a sort of real world example here. So on the bottom here, this layer, we have an older sandstone layer, and you can see that the layers aren't horizontal. They're actually tilting, they're dipping. The bedding is non-horizontal. And then we have a younger layer here. This would be like a sedimentary breccia. And the layering, the bedding is very crude, but in general, it's approximately horizontal, as you can see here. And then finally, we have this sort of sharp knife edge boundary or geologic contact between the tilted sandstone layers underneath and the horizontal sedimentary breccia up top. So what's going on here? Well, the older sandstone layers are now tilted, but keep in mind that when they were laid down, they weren't tilted, they were flat, and they've only been tilted after they were laid down. the younger sedimentary breccia, as we mentioned, has crude horizontal layering. In this case, the upper layer hasn't been tilted. So can you see that that's going to imply then that these older layers were tilted and even eroded along this boundary before the upper layer was ever there to begin with. And by the way, this particular boundary that I'm kind of highlighting in red right now, it's what's called an angular unconformity, and it separates older layers tilted at one angle from younger sedimentary layers tilted at a different angle, or in this case, not at all. So how does an angular unconformity develop? It's actually a fairly straightforward sequence of several different things happening. So let's briefly go through this. So the first thing that happened is the older sandstone was deposited, and the layers, as I mentioned, were originally horizontal. And after that, and this is before the younger breccia ever existed, there was some sort of mountain building event that tilted the layers. And so the older sandstone layers become tilted due to their being caught up in a mountain building event. And then maybe for millions of years, maybe for billions of years in some cases, that older layer is eroded. Perhaps the mountains are entirely eroded away to create this ancient irregular erosion surface. And then only after the erosion stops is the younger sedimentary breccia deposited on top. And so again, this boundary between the older tilted layers and the younger non-tilted layers is called an angular unconformity. And the reason we care about angular unconformities as geologists is that they're evidence of ancient mountain building. This is literally how we recognize ancient mountain building in the geologic record. We look for angular unconformities. So it's really important to study this slide and to be very familiar with the steps involved in forming an angular unconformity. Okay, another principle, kind of straightforward, I think, is called lateral continuity. And that is just to say that when sedimentary layers are laid down initially, they're like blankets that stretch out in all directions horizontally over the landscape. In other words, these sedimentary layers are laterally continuous from one place to another. And we can recognize that even when the layers are eroded here and here, that's an erosion surface. But notice that this layer, this sort of dark layer, it's probably a shale, something like that, corresponds to this other layer on the opposite side of the valley. Clearly, this layer and this layer were once physically connected. That is, they were once laterally continuous. And it's only later that all of this intervening material has been removed by erosion to create the valley in this case. And we typically see this. Here's a road cut where we can see layer by layer the fact that over maybe a few tens of meters, these layers are laterally continuous. Okay, on to the principle of inclusions. An inclusion is just a fragment of an older rock included within a younger rock. So that's important. The rule of thumb here is that the inclusions are always older. The host rock that the inclusions are in is younger. So over here on the left, we have a granite, and this would be like a sandstone over here. What if I didn't label, the relative ages of the granite and the sandstone? How would you know in this case that the granite is older than the sandstone? Well, you'd know it because here we have granite inclusions in a sandstone host. So that tells us that the granite was here first, and this is actually an ancient erosion surface right here. And that granitic terrain eroded for perhaps millions of years. And then at some point, the area was probably flooded with water, if this is a river-borne sandstone. And as currents were sort of flowing over the ancient granitic riverbed, for example, the currents ripped up pieces of the older bedrock and incorporated those fragments, those inclusions, within the younger sandstone. What about the right-hand diagram? Well, superficially, they look alike, but it's actually the opposite over on the right. In this case, we have sandstone inclusions in granite. So what this tells us is that the sandstone was actually older and the granite came later. How might that happen? Well, what we're seeing here, this boundary right here, what's called a geologic contact, this contact is an intrusion. It's an intrusive contact. So in other words, the granite blobbed its way up into the sandstone from below when it was still a magma, when it was still hot and liquid. And then in this case, a few fragments of the sandstone sort of fell down into the granite to become sandstone inclusions in granite. So the principle of inclusions can be really useful in helping us to recognize older versus younger rock units. Here's an example of an older mafic igneous rock inclusion within a younger, more felsic host rock. Okay, on to fossil succession. The take-home message here is that very often the fossils in a sedimentary rock can be useful when we're trying to establish relative age relationships. But to understand the logic here, it takes a little bit of explanation. So let me kind of walk you through it slowly. In this case, we have a cross-section, a vertical slice, and we know at a moment's glance that layer A is younger than layer B. Not because of the fossils. We don't even care about the fossils at this point. We know that layer A is younger than layer B because it's sitting on top. Hey, remember, that's the principle of superposition. Okay, here's where the fossils come in handy. When we look at layer A, we find that it contains all of these different fossils. This one, and 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 this one. That's the fossil content of layer A. And so the cool thing is, once we've established that this is the fossil content of layer A, it means that anywhere else on Earth, if we find a sedimentary rock layer with those same fossils, it allows us to say that that other sedimentary rock layer is approximately the same age as layer A. And likewise, somewhere else in the world, if we find some random sedimentary rock with the same fossils as layer B, we know that that other layer is approximately the same age as layer B. In other words, the fossil content of a rock helps us date the rock. So let's work through the logic. We've kind of done this already, but here it's more explicit. We know that layer A is younger than layer B, thanks to superposition. And we also know that layer A has a distinct mix of fossils. So does layer B, for that matter. So again, anywhere in the world where we find a rock unit with these fossils in it, we know that that rock unit is the same age as layer A, and similar for the fossil content of layer B. So as an example, here's one location, and we have a distinct mix of fossils that kind of changes upward in the sequence from older to younger. And then what if we were to go somewhere else? It could be a few miles away. It could be thousands of miles away. Hey, can you appreciate that if we find the same fossil, or more likely the same mix of fossils here as we do here, then it tells us that for layer 3, this rock unit and this rock unit are the same age. And that's true, by the way, even if the two rock units were never in physical contact. Notice that the patterns here are different. This sort of bumpy pattern, that's the typical pattern that geologists use for sandstone. And then over here, this sort of brick pattern is the standard pattern that geologists use to represent limestone. So over here, we have a sandstone. Over here, we have a limestone. But the take-home message is, in this case, that because the sandstone and the limestone have the same fossils, we know they're approximately the same age. And same with layer 4 and also layer 6. So that's, in certain situations, how we can use the fossil content of a sedimentary rock to help us work out relative age relationships. That's called the principle of fossil succession. One of the most important relative age dating principles is known as cross-cutting relationships. And here, the rule of thumb is kind of opposite to that of the principle of inclusions. And the rule of thumb here is that the feature doing the cutting is always younger than the thing being cut. Let's focus on the relationship between fault A and the sandstone over here. Notice that the fault slices through the sandstone, and along the fault, the sandstone layer is shifted. To the left of the fault, the sandstone layer is shifted downward. To the right of the fault, the sandstone layer is shifted upward. So if I sort of take away my annotations here, you can kind of see that better right here. Clearly, the fault cuts through the sandstone rather than the other way around. So what does that mean about the relative age of the fault versus the sandstone? Well, it just means that the fault is younger than the sandstone. See how that works? It's sort of like cutting a cake with a knife. The cake has to exist before you can cut it with a knife. Therefore, the cake is older than the cut that you make. Okay. The same thing is true with intrusive relationships as well. So here we have that same sandstone layer, and we have a sort of sheet-like intrusion called a dike. And if we focus right in here, can you see that it's the dike that cuts through the sandstone, not the other way around? So what does that mean about the relative age of dike A versus the sandstone? Hey, it's got to mean that dike A is younger because it's cutting through the sandstone rather than the sandstone cutting through the dike. Okay, so that's a quick introduction to cross-cutting relationships. Now what I'd like you to do is just focus on these three features over here, the batholith, dike B, and fault B. A batholith, by the way, as you can read down below, is just a large igneous intrusion. So the batholith was essentially once a magma chamber, or actually a whole bunch of magma chambers, but we won't worry about the details here. In general, for this problem, think of a batholith as a large igneous intrusion. And as I said, think of dike B as a smaller sheet-like igneous intrusion. And then there's fault B. So which came first, which came next, and which came next? Which is the oldest feature between these three things? Which is the intermediate feature in terms of age? And which is the youngest feature? So I'm going to pause for maybe 10 seconds to kind of let you work out the relative age relationships on your own between the batholith, the dike, and the fault. Okay, were you able to do that? We'll go through it anyway in the next slide. Okay, so here we go. Here's the answer right here. And this is typically how we list things, kind of like superposition. So the fault is the oldest. How do we know that? We know that because the batholith intrudes the fault. The batholith has melted away the fault in this area, so we know the batholith is younger than the fault. We also know that dike B has melted away the fault in this area, so that tells us that dike B is also younger than the fault. So the fault is the oldest. How about now between the batholith and the dike? Which comes next? Well, and let me clean this up a little bit. You can probably see right here, let me ask the question this way. Does the dike cut the batholith, or does the batholith cut the dike? And you can probably see, if you stare at that a second, that it's the dike that's cutting into and through the batholith. as the dike intruded the batholith right here, it literally melted away the batholith and replaced it with dike B material. And then it's also the case that dike B, of course, as we said before, kind of melted away the fault. So we know that dike B cuts the batholith, not the other way around. So fault is first, then the batholith, then dike B. My suggestion when you're working out these cross-cutting relationships, I find it easiest to start down near the bottom of the diagram and kind of work my way up rather than from the top down. There are different schools of thought on that, but I just find it personally easiest to first identify the oldest rock unit and then generally work my way up towards the top of the diagram to find increasingly younger rock units. Here are just some other examples. This is a cross-section that I saw along the highway coming back from Big Bear a few years ago. And in this case, we have some granitic host rock, that's the oldest, and we have both a dike here and here, and a fault. And it's just a textbook example. Can you see that the fault cuts through the dike? This dike used to be continuous. And then because the fault moved like that, the right side of the fault moved diagonally upward, and the left side of the fault moved diagonally downward. And it offset or shifted the dike in the process. Okay, so getting rid of all this, can you see that if we're describing this, we would say that the fault cuts through both the dike and the granitic rock. So that makes the fault the youngest feature. On the other hand, the dike cuts into and through the granitic rock, but it doesn't cut the fault. The fault cuts the dike doesn't cut the fault. Again, you can't cut something that doesn't exist yet. So from oldest to youngest here then, we have the granitic rock, which is the oldest. Next comes the dike, and next comes the fault. As I was kind of mentioning before, sometimes we see features called unconformities. Unconformities are just gaps in the geologic record. And these gaps are created either by erosion or by non-deposition. And there are three types that you want to be vaguely familiar with. They're called disconformities, angular unconformities, and nonconformities. A disconformity is essentially an unconformity that's parallel to both the top and the bottom layers, for the most part. An angular unconformity reveals an angular difference between the older layers underneath and the younger layers up top. And then a nonconformity is where we're actually mixing and matching rock types. In the case of a nonconformity, we have igneous or metamorphic rock on the bottom and sedimentary rock up top. Notice that for these other two, we have sedimentary rocks above and below the unconformity. Okay. So just like we saw a few slides ago, here's the older rock, it's tilted. Here's the younger rock, it's not tilted. This is the angular unconformity. This is the ancient surface of erosion that separates the older sandstone from the younger sedimentary breccia. And this is the one I want you to be very familiar with. How come? Well, you might remember from a few slides ago, angular unconformities are how we recognize ancient mountain building in the geologic record. That's kind of mind-blowing if you stop and think about it. You know, we're used to thinking of mountains as forming right now, you know, before our very eyes at convergent plate boundaries. But the same thing happened in the geologic past, but it might be that those mountains are so old, they're so ancient that they've been completely eroded away only to be covered up by much younger sedimentary rock. How could we possibly know that? How can you possibly know anything about an ancient mountain range that's not there anymore? You know it because very often in the geologic record, we can recognize angular unconformities. That's how we know about ancient mountain building. You can read about this in the ebook, my story about personally visiting Hutton's Unconformity in just outside of Edinburgh, Scotland, a number of years ago. It's kind of a sad story, but you can read about it in the ebook. This, by the way, is arguably the most famous geology photo you'll ever see in your life. James Hutton, who we've talked about, he's the father of modern geology. He was the guy, he was the person who figured out in the late 1700s how angular unconformities develop. So what Hutton realized is we first had deposition of the older sandstone, and then we had uplift and tilting and erosion, and then we had deposition of the younger conglomerate, and also what's called this red sandstone locally. And then we had a second period, in this case, of tilting and uplift and eroding. And the reason we know that, the reason that we know that there's not just one, but two episodes of uplift and tilting is that because both the older and the younger layers are tilted. So the first tilting episode tilted these older layers a little bit, and then later deposition deposited these younger layers that were horizontal. And then a second period of tilting came along, and it tilted the older layers even more, and it tilted the younger layers into their present position. So there's a lot going on in this slide. It reveals a pretty intricate geologic history. But the point is, if we apply the principles of relative dating, we can make sense of that geologic history. That's pretty cool. Okay, here's one last slide just to, you can use as a simple concept check. So we have this cross section below, and then I've labeled various rock units and features. The thing you want to know, and I would always tell you this, in this case, all of the layers are sedimentary rock, so there's no igneous or metamorphic rock anywhere on the diagram. L and M are cracks or fractures along which movement or shifting of the layers has occurred. Those are called faults. And then layer S, which we just got through talking about, is what's called an unconformity. In this case, because the layer or the unconformity itself is kind of parallel to the layering above and below, this would be a disconformity, but don't worry so much about that. Okay, let me remove these annotations here and give you a second. So what do you think? Which sequence is correct? Is it this one, or this one? I'll give you a few seconds to kind of decide which of these three sequences is correct, and we'll go from there. Again, my recommendation, start down at the bottom, identify the oldest layer, and then kind of progressively work your way up toward the top of the cross section. I think that's, for me anyway, the easiest way to solve these cross sections. Okay, well, what did you come up with? And a lot of times on multiple choice questions like this, it's very easy to eliminate certain choices right off the bat. We know, for example, right, that J is not the oldest layer. J is the youngest layer, or one of the youngest features on the diagram, if not the very youngest. So we can eliminate that. So we're just down to this one or this one. Is it this or is it this? And if you work things through and apply these relative age relationships, these different relative age principles correctly, it turns out that that's the best choice. So A is the oldest, then C was deposited on top of A, G was deposited on top of C, and then P was deposited on top of G. And then along comes fault L. So far we're there. But notice in this case that the unconformity S erodes away and cuts the fault. So that means that S is younger than L. And then after that, B is deposited on top of S on both sides, and then D, and then J, and then finally M is the younger fault. Okay, that's all for this PowerPoint. We'll move on to absolute dating after this.